Hello everyone, in this lecture we will be solving 1987 IMO problem number 4. Here's a view of this problem. We would like to show that there's no function f from the set of non-negative integers onto itself which satisfy the following functional form. In fact, I would like to replace the number 1987 by any positive integer c and focus on a more general problem. So new problem would be to find for which values of c, recall c are positive integers, and there exists a function f from natural numbers onto itself, and including 0 here, such that we would have this condition f of n. I replaced the 1987 with c for n in natural numbers. So let's go ahead and fix c, an integer c greater than or equal to 1, and let's assume f is such a function that works. Then we should have that by just simple observation. Notice that f of consider this expression, f of r plus c is equal to, I can replace r plus c with f of r, right? So therefore inside will become f of r, like that. But notice now that it's as if I'm plugging in f of r instead of n in this expression, right? So that would simply translate as f of r plus c for r. Again, r is a positive integer. And in fact, I can keep repeating this procedure. For instance, let's try it one more time. R plus 2c, right? That one would simply be equal to f of r plus c, right? So basically what I did is I just replaced, so I rewrote this as r plus c, and not recalling the definition here, it's as if I replaced the n with r plus c. That's my n. So as a result, I can just rewrite it like this. But then with a small twist, again, I would just realize that this thing, by a simple reinterpretation, so consider plugging this into my expression, the n here, like we did previously, we would get that f of r, so f of r plus I believe 2c, right? So, well, why? Because when we plug it in, it would just give us f of r plus c, but f of r plus c, previously we found out that it was f of r plus c, so we would have f of r plus c, which is f of r plus 2c. So we can proceed inductively, right? So proceed inductively, let's say. So as a result, we would find the more general form, f of r plus c times q. If we repeated q times, we would realize that that would simply be equal to f of r plus cq, where again both q and r are positive integers. This kind of reminds us of, so because if you consider this number like an n, it kind of reminds us of the division algorithm here. So as a result, this brings us to the following thing. So let me proceed carefully. So let's consider this set cap c, integers from 0, 1 all the way to c minus 1. So anytime we pick n in this range, right? So in from this set, then and also letting g of n and h of n, let's say, and h of n represent the quotient and the remainder. When f of n is divided by c, we get this awesome result. So we get that f of n is equal to, using our the definition, so c the division algorithm, I should say, C times G of n. Yes, like that. G of n, which is the quotient, can be anything actually, is an integer, positive integer. However, the remainder h of n, which is the interesting guy here, has to come from this set C, because when we divide f of n by C, the remainder will end up in this range. Okay, so now if I apply this previous result that we got earlier, this one that we got inductively, with Q being equal to G of n and R being equal to H of n, we would get the following result. So f of n, oops, sorry for that, f of n, that thing would be simply equal to f of n, I'm just applying the definition here, f of h of n plus c times g of n. In this case, our q is g of n, so g of n. But notice that our function f is mapping positive natural numbers to positive natural numbers, so this expression here is definitely greater than or equal to c times g of n. Now, upon a second observation, for instance, if you have a look at the very earlier definition, f of n is equal to n plus c, and reminding ourselves that because we picked n in C to begin with, that's how we started our thing, as a result, this whole thing is less than 2C. So let me change the color of my pencil, and so therefore what this says is this expression here is strictly less than 2C, so let's carry it over here, strictly less than 2C. So compare these two sides now. So C times G of n is strictly less than 2C. What this implies is that G of n is equal to 0 or 1. This naturally enables me to partition the set C, in fact. So this set C into two sets, C sub 0 and C sub 1. So I can partition such that they are both defined as follows. So C sub 0 is all those n's in C such that G sub n is equal to 0. And in a similar way, C sub 1 is equal to n in C such that G of n is equal to 1. Now we have apparently two cases to consider, right? So if case 1, n is in C sub 0, then in this case, f of n is simply equal to h of n, right? So because g of n becomes 0, so in this expression here, this is our main expression, so g of n vanishes and we have f of n equals h of n. And from here, if we apply the very early on definition, so this would imply that f of n would be equal to, well, obviously because, well, two things. Because f of n is just h of n, so it is f of h of n, but at the same time, f of n by definition was n plus c. Now what I will do is, this time I will apply the division algorithm to f of h of n, so to this guy here. If I apply the division algorithm and I divide it by c, we get a quotient of 1, so that's the quotient, so you can just say times 1 here, and the remainder is apparently n. So you have, so therefore what I'm trying to say is that, referring back to the definition for h of n and g of n, we apparently, so this implies that g of h of n, that one is simply equal to 1, and h of n is equal to n for if n is in C0. Now, in a similar way, in case 2, I will do a similar analysis. Case 2, we are in the case where n is equal to C1, suggesting g of n is equal to 1 here, don't forget. So therefore, we have that f of n is simply equal to h of n plus c times g of n, but g of n is 1, so plus c actually. So if, like we did here, right? So if we apply the definition, the early definition, we know that n plus c is equal to f of n, but notice here that f of n is just h of n plus c, and moreover that is equal to f of h of n plus c. Recall that this last equality follows from the fact, so this one follows from the fact that f of r plus c was equal to f of r plus c, as we pointed out earlier, somewhere here in the very first stage, right? So early on we just realized that. Okay, so going back to our analysis, f of n is equal to, well, actually have a look at these two. Okay, so this is easier to handle. So this would imply that f of h of n is simply n. The c's will cancel out, so we would have an n here. So therefore, what it implies is, like in the previous case, remember the case 1, so let me just remind you of case 1, which we got this very awesome result. In this particular case, g of h of n, when we apply the division algorithm to h of n, we realize that quotient is 0, and the remainder h of n is simply equal to n here, right? So because you can think of this as 0 times c, and I think, yeah, that pretty much does the trick here. Focus on the function h, please. So if you have this one, oh, sorry for that. So for n in c1 here, and look at this one. So when you look at the function h, so the function h is defined from c to c, because the remainders are always end up in this range, such that we have the following very, very nice feature. So in both cases, we got that h of n is equal to n, first of all, and secondly, which is the more surprising result, if n is in C0, then in that case it implies that h of n is in C1, so surprisingly enough, and when n is in C1, then it implies h of n is in C0. Let me remind you again where we got this. So remember that when n is in C0, which is case 1, we realize that h of n is in C1 because look at the value of g. In that case, it's 1, so it ends up being in C1. And when n is in C1, which is the second case, it turns out that g of h of n is 0, which means h of n is now in C0. So h of n is equal to n for n in C. So this first observation lets us know that our function here is one-on-one, one-to-one mapping of C onto itself, right? So, and the secondly, the second condition implies is very strange. So it basically tells you that h will map C0 onto C1, but remember the function itself is one-to-one, and also it will map C1 onto C0. So basically, what this says that because we are mapping these sets onto each other, and the function h itself is one-to-one, this immediately should imply that C0 and C sub 1 should have the same number of elements in them. So, but there's only one explanation for that, right? Which is that C, number of elements in C, which is because C sub 0 and C sub 1 are disjoint sets, they have no intersection. I don't have to write, or if you want, let me just do it anyways. So this guy is not happening. So, and these two have the same number of elements. So let's say 2 times C sub 0, or doesn't matter, you can say 2 times C sub 1. But what it tells you that the C is an even number, so our set should have an even number of elements in them. But remember the definition of our set C, it was 0, 1 all the way to C minus 1, so it had C elements in them. So C is an even number. C is even. And that brings us to the conclusion that our function, the original, so we can now go back all the way to the top, and when we think about the solution of this problem, now we know the answer. The answer is that this functional form defined as f of n equals n plus c will only exist for even valued c. So we can say that the answer is when c is even. But notice that 1987 is an odd number. As a result, no such function f will exist, and we are done.